In our last activity, you have tried formulating a linear programming model from a case situation. In this video, I'd like to show to you how to compute graphically a linear programming model with two variables. This example is found in our textbook, The Operations Research by Hamdy A. Taha. Recalling the general format of an OR model, it should have an objective function subject to identified constraints. Here presenting to you the linear programming model for the Reddy Mikks case situation. This part is the objective function subject to several constraints or limitations. Let's interpret the model. The objective of the company is to maximize its profits through its two products, namely the interior and exterior paints. The unit profit for 1 unit of exterior paint is $5,000, while the unit profit for 1 unit of interior paint is $4,000. Reddy Mikks used two raw materials, M1 and M2, to use for those paints. The exterior paints needs 6 tons of raw material 1 and 1 ton for raw material 2. The interior paint needs 4 tons of raw material 1 and 2 tons for raw material 2. The maximum daily available supply for raw material 1 is only 24 tons, while for raw material 2 is only 6 tons. It means that the usage of raw material 1 by both paints is limited only to the maximum raw material availability, which is expressed mathematically with the inequality sign less than or equal to. Another constraint was given that the daily demand for interior paint cannot exceed that for exterior paint by more than 1 ton, which can be translated in this equation form. And lastly, the maximum daily demand for interior paint is 2 tons. We also need to put the non-negativity constraints, the x1 and x2, which are greater than or equal to 0. Again, Reddy Mikks wants to determine the optimum product mix of interior and exterior paints that maximizes their total daily profit. So to graphically solve for the optimum solution, we determine the feasible solution space or feasible region. We first replace the inequality signs to equal signs as expression of linear graphs. And then we create the first quadrant of a coordinate plane with horizontal axis as x1, which is the exterior paint, and the vertical axis as x2, and that is for the interior paint. Let us graph the four constraints by setting a variable from each equation to 0 and compute for the other variable, including the non-negativity constraints. Next, consider the effect of the inequality. All it does is divide the x1, x2 plane into two half spaces, one on each side of the graphed line. Only one of these two halves satisfies the inequality. To determine the correct side, choose 0, 0 as a reference point or corner point. If it satisfies the inequality, then the side in which it lies is the feasible half space. Otherwise, the other side is. The use of the reference point 0, 0 is illustrated with the constraint 6x1 plus 4x2 is less than or equal to 24, because 6 times 0 plus 4 times 0 is equal to 0, which is less than 24. So the half space representing the inequality includes the origin. So the non-negativity constraints bounded the solution space. The solution space we are referring to is what we call the feasible solution space. The feasible solution space is delineated by the line segments joining the points A, B, C, D, E, and F. Any point within or on the boundary of the space A, B, C, D, E, F is feasible. That means all the constraints are satisfied simultaneously. Further, if we found a point of x1 and x2 that lies outside the solution space, that means that that point is an infeasible solution because a constraint or constraints have not been satisfied. Because the feasible space A, B, C, D, E, F consists of an infinite number of points, we need a systematic procedure to identify the optimum solution. The determination of the optimum solution can be identified through the direction in which the profit function z is equal to 5x1 plus 4x2 increases. We can do so by assigning arbitrary increasing values to z. For example, using z is equal to 10 and z is equal to 15 would be equivalent to the graphing the two lines. Thus, the direction of increase in z is as shown in the figure. Therefore, the optimum solution occurs at c. The values of x1 and x2 associated with the optimum point c are determined by solving the equations associated with lines 1 and 2. The solution is x1 is equal to 3 and x2 is equal to 1.5 with z which is equal to 21. This calls for a daily product mix of 3 tons of exterior paint and 1.5 tons of interior paints. The associated daily profit is $21,000. The optimum solution can also be found simply by enumerating all the corner points as the following table shows. As the number of constraints and variables increases, the number of corner points also increases, and the proposed enumeration procedure becomes less tractable computationally. Nevertheless, the idea shows that from the standpoint of determining the LP optimum, the solution space A, B, C, D, E, F with its infinite number of solutions can in fact be replaced with a finite number of promising solution points, namely the corner points A, B, C, D, E, and F. This result is key for the development of the general algebraic algorithm called the simplex method, which we will study in the next module.